I'm here now to command everyone's attention and settle you all down. And if you have a drink, excellent. This is a good time to go in. If not, but Evelyn has asked me to start with the talking and the presenting and the what have you. So I'm Frank McSherry, as the slide indicates. I'm delighted to be here. I'm visiting Berlin for a few months, and it's wonderful to stop by Data Artisans and spend some time with them talking about the problems that they have. It's great to have the opportunity to tell you guys a little bit about the sorts of things that I do and that I think are interesting. And I'm going to do some of that now. And I should say at every point along the way, you should feel more than welcome to interrupt and ask a question. I will do my very best. You should remind me to repeat the question, and then I will answer it. Or I will defer it until much later in the talk until you've forgotten about it and I've had some more to drink, and then you get a different answer. So my plan is to tell you a bit about things that I think are interesting. This is going to start with some of the motivation for the recent work that we've done. The title of the slide is Timely Dataflow. This is the name of some work that I had done recently with collaborators at Microsoft Research in Silicon Valley. And to be totally honest, the rest of the talk isn't going to talk too much about it, but I've been so used to putting this as the title of slides, I don't really have a better backup title for my slides. So this is sort of a general umbrella of data flow research that's gone on that is timely in a few senses. It's timely in the sense that it's useful to be doing this at the moment. Like it's good from a research point of view to actually kick the data flow community and get them doing some new stuff. It's also very aware of time and the use of time in data flow to make things move a little bit faster and what have you. So let me start. Again, interrupt at any point if you don't like what I've said, or if you think I've said it wrong, or you just would like to say your own thing. Data parallel, data flow. I suspect most of us here like data parallel, data flow. Yeah, that's sort of why we're here. There's a few cool things about it that I think speak to a lot of people. These are things that I think are interesting. It typically comes with a very simple programming model. So the mental model for how do I make 100 computers interact with each other is not nearly as complicated as it used to be, when you actually had to tell the 100 computers how to actually interact with one another. It was very painful. At the same time, the restrictions that data parallel data flow imposes results in some fairly performant implementations. The computers aren't going to do any arbitrary thing. They do fairly structured things in batches, and there's a relatively focused amount of computation that they need to do so they can make sure to do it well. So that's great. I'm going to argue, or at least I'm going to talk a little bit for a little while about some changes I'd like to make to this, and there's some really fun animations that Keynote lets me do. I think that currently the programming model is a little too simple. Or I'm gonna, before people jump up and kill me because it's already complicated enough. What I mean is that there's a difference between a simple programming model, one that has a relatively small set of things that you can do, and an easy programming model, one where you can quickly do the thing you want to do. And I'm going to try to draw these distinctions and show that there are several things you might like to do in data flow. They're actually a little annoying and sort of hard right now, and you have to trick the data flow system in order to get them done. Whereas if we had sort of integrated them or embraced them a little bit more closely, the data flow system would just take off and do them for us, and we wouldn't have the problems we occasionally have. Sort of hand in hand with this, though at some level it's another issue, is that the implementations suffer a little bit, especially if you're not able to express the task you want to do. You have to, again, trick the data flow system. You might have to, to do iterative computation, you might have to restart the same computation multiple times if you're not using something that supports cycles. That's annoying. And it results in a system that doesn't run quite as well as it might. I'll show a few examples as we go along where if the system knew that you were trying to do the sophisticated thing that you're trying to do, it would just zip along real quickly. But since you're not allowed to tell it, things go slowly. So these are the two things that I'm currently excited about. Is making programming models a little bit more accessible and making things go fast. So just to be totally clear, that's the world that I live in at the moment. There may be other people here like, no, that's not interesting. I like machine learning and things a little higher up on the stack. In which case, hopefully you'll appreciate that things going faster is good, but I'm not going to make your life necessarily much better by giving you a new exciting collection of tools that will make machine learning better for you. I'm going to start with some background. I like these slides mostly because they're a little punchy and fun, and since I'm not employed at Microsoft anymore, I'm allowed to say what I think, which is good. So this is some data that was taken from an OSDI paper in 2014, where some folks from Berkeley talked about a system called GraphX. I don't know, how many people here are familiar with graph processing systems and the current crop of stuff out there? Yeah, okay. So there's a few systems you can use for graph processing. They of course, they looked at some that they were familiar with. These are mostly Berkeley or Bay Area oriented graph processing systems. Spark, Giraffe, GraphLab, GraphX. They're intended for doing, well, sorry, Spark is not intended for doing graph processing, but you can do graph processing on it. And the other systems are sort of graph focused. And GraphX was the new subject of this particular paper. And so they did some measurements, and they reported some measurements here. These are all taken from their paper. Of what happens if you turn on a bunch of cores in their cluster and you say, I want to do 20 iterations of PageRank on a few different graphs. And these are some graphs that people like measuring because they're sort of nice reference graphs. And one of the conclusions that they took away, there'll be some more numbers, but was that GraphX really is not much worse than GraphLab, which is sort of the state of the art at the time. But it's as general and flexible as Spark, which it substantially outperforms. So that's great. GraphX is a success, right? Well, that's fun. And if you look at these numbers, you might agree with that. There's a system that they didn't compare against, not some exotic system. They failed to compare against a laptop, my laptop in particular. My laptop has achieved some notoriety of late. So you turn on a laptop with one core, and you write a 10-line program to compute PageRank, 20 iterations. It's a for loop. It goes from 0 up to 19. And then it loops over the edges in the graph. And you run it. And it takes about this much time. Which you might say, oh, that's possibly a little surprising. I would have thought with 100 times the resources, maybe these, and more than 100 times the engineering over my 10 lines of code would have done better. And they don't. And that should raise some eyebrows. You can, if you'd like, you can tweak the 10 lines of code and make it maybe like 50 to 100. And the numbers get better. So to the point where they're clearly outperforming all of the systems for all of the data sets. So maybe PageRank's a fluke, who knows? They did this also for graph connectivity. So there's it's this label propagation algorithm, if you're familiar with that. Excellent, I won't belabor the point. I'll tell you a bit more about it later in the talk. But. So again, bunch of cores, some data sets. You can see Spark and Giraffe on the large data set, they actually run out of memory on a cluster that has a terabyte of memory in it. So they take over 8,000 seconds because that's when they stopped running the computations. And you can run the same algorithm on a laptop. It's just this iterative graph processing algorithm where people repeatedly tell their neighbors about who they can be reached by, basically. And yeah, right. So this is not so great. Or it makes you wonder what's going on. One thing that's going on, by the way, is this label propagation algorithm that they use. It's sort of a darling of the graph processing community because it fits in this think like a vertex mental model, if you've heard that meme before. But it's a horrible algorithm, actually. Graph connectivity, if you ever took undergraduate computer science, it's something that people have been studying for about 40 years. 40 years, 90 years. So Borufka, back in the 1920s, did some graph connectivity stuff to lay out the electrical network of the town that he lived in. And so their algorithms, there's really simple algorithms, linear time, just scan once over the edges in the graph, and you just write those down, and they're really fast. And you just look at some of the numbers here, and apparently my laptop, you multiply all the things together, is 4 orders of magnitude more efficient than Spark doing graph connectivity computation. And I don't know. Right, so what were these people were the people that we had pointed as like, oh, brilliant. You guys are the best, most qualified people to design scalable distributed systems that are going to make the best use of all of our data. And it turns out that you go 100 times faster just running on your laptop. That's not right. Something went wrong here. And coincidentally, I'm going to tell you that it's because the programming models that they're using are a little bit too simple. Like they're too primitive. You can't write the program you want to write. And in ways that I really can't explain, their implementations are funny. By the way, I'm going to pull up some Flink performance numbers a little bit later on. So hope you guys get your beers now and start drinking. So let me just recap briefly the things that we're supposed to be good at in data parallel data flow. What is it that we think we know how to make computers do very well? And we'll go through each of those things, and we'll arrive at a point and I'm going to try to convince you, this is actually a pretty good point. We should be able, we're at a position where we should be able to make things go fast. Or at least, efficiently, whatever. Sorry, that should have been up before. So way back when, 10 years ago, there was this MapReduce paper, and if you're familiar with data parallel computation, actually it was like 30 years ago or something like that, but in the popular eye was captured by MapReduce, which suggested one way you can write programs, if you'd like, is you have your little main method here, and what it does is it takes a pile of input data, and you describe, here's something you should do to each record. You should produce some keys and some values, and if you, dear system, are nice enough to go and shuffle the data for me so that all of the values with the same key live together, here's a function you could run for me. All right? And this system says, that's great. If you tell me these instructions, I can go and do this in parallel across lots of machines, and really I'm quite, I think that's good, right? It's either very bad or it's nice and contrasty. Oh dear. Oh. So this is nice. This is parallelism, basically. Here we are. Parallelism, right? So we know that we can make lots of computers efficiently operate in parallel if we give them explicitly parallel instructions. We know how to make computers do that really quite quickly. We send the instructions to the computers who already have the data, and they run surprisingly fast. Good. This evolved a little bit, and people said, okay, that shouldn't have been your main method. You just make that a function, right? And you can call that a few times. Put your main method somewhere else and call myfunc 2 or 3 times, maybe a few other functions if you like to. This is sort of, I think of this as Dryad link showing up and building up slightly more interesting and complicated data flow graphs. But basically, it's still batch processing. It's still just exploiting parallelism for us. All right. At some point, some smart person said, well, actually, why not just keep things live? At some point, I mean, again, 20 or 30 years ago. Keep things live, and what we'll do is we'll push records into the source, into the input data set there from some exogenous source. This is state, basically. We've understood that we can turn on these MapReduce vertices and keep them running. Right? We don't have to throw them away. We can just keep them running, and we can feed records to them. And that's great. We've now moved from batch data flow to streaming, apparently Dataflow. Wow, okay. That's going to be fixed. There will be no evidence. Oh, geez. So streaming Dataflow, trademark, is, seriously, it's actually like GraphLab, the company, is now called Dato, so I'm in like deep trouble, actually. Streaming Dataflow is basically the observation that not only parallelism, we can keep state up and running concurrently. I mean, this isn't a big mystifying observation that computers have memory, and in the absence of you doing anything crazy with them, they're going to keep that memory how it was just before. But the observation that this is actually useful, that we can write new and interesting types of computations that behave differently than the batch computations is exciting. And state is one of the things we're going to add to our pile of exciting popping elements. And there's one last thing, which is that rather than just run that silly function and pipe its results out to some stream somewhere else, we could bind that to a variable, call it output, and instead of reading data from the source, we could actually be reading data from this output, feeding it back into the data flow. And at this point, hopefully we have a slightly better spelled title. There we go. All right. So we have iterative data flow. So this is now iteration that we've added in as a new feature. And again, this is something that we can do relatively efficiently. We believe we know how to take data out of the results of one of these streaming computations and put it right back in about as quickly as you might imagine. There's no fundamental reason that should be going slow. And these 3 things, state, iteration, and parallelism, are pretty powerful. Like if you think about what is it that I really want my computer to do, and I'm trying to build a parallel scalable compute thing, I need to be able to get the computers to run concurrently. I want them to keep some memory around. I want them to be able to do loops. What am I missing? Am I missing anything? And I think the answer is no. I don't think you're missing anything, right? If you have a bunch of computers that have state and can chat with each other with low latency, you basically have computers with a network and memory, right? You're not getting much more than that. So there's no particular reason, if we can do each of these things well, that we can't make general data parallel computation go promptly and efficiently. And by general data parallel computation, I do mean something slightly more general than just data flow. So data flow is nice, you have directed edges. I'm hoping, and I'm not going to convince you through the course of this talk, but I'm hoping to elevate a little bit what people think about as possible when they think about doing parallel computation, data parallel computation in particular. So I'm going to give some examples. Before I give the examples, sorry, I'm going to motivate each of the examples using important bullets. So why was there not a round of applause when I put those three things up before? We're not done. What's keeping us from actually achieving our wonderful supreme goal of fast data flow systems that are very easy to write programs against and go incredibly quickly, and everyone's happy. So there are two things, at least two things, but two things that I'm going to point out as missing that I'd like people to, either like pay more attention to or just acknowledge, like, oh, yep, that's too bad. Your choice, obviously. One of them is structured programming languages. So the types of data flow programming that we have at the moment, I'm going to say are roughly analogous. Iterative data flow. It's roughly analogous to trying to write a program on your computer where you get one while loop and a bunch of if-then-else statements, as many of those as you want. But basically, your control flow is one big loop, and that's how you have to write your program. You can write a program that way. It's Turing complete. It's totally fine. There's no fundamental limitation about what you can compute. But the ease with which you can write something, and the ease with which you can explain to, for example, a compiler, what's going on in your computation, how to run it, how to schedule it, how to get certain things done quickly, what the modular substructures are in your program. So for example, then the one that I'm going to bring up as an example, and it might be that it's the only example, I apologize, is nested iteration. Right? If you want to write a subcomputation that does its own iteration and then returns, how do you do that, right? I mean, you can, like what Giraffe does at the moment is they have this central sort of master logic that dishes out essentially PC instructions, right? It tells you what are we currently doing at the moment, guys, and you tell everyone what you should be doing at the moment. Everyone fakes out like there's some different type of vertex than they used to be, and it's just gross, and it doesn't go very fast. I'm going to show you going fast, I promise. The second thing that I think is missing, or at least that I'm going to complain about for a little bit, and show you some evidence that we can get around, is this issue of zero overhead implementations. So the implementations that we're dealing with, they're nice. They're at a higher level of abstraction, so you can write high-level statements like joins and group bys and maps. But it comes with a bunch of overhead, and I'm going to try to explain not necessarily where that overhead comes from, but that you can avoid it, and potentially, you can look and conclude, wow, that's appealing. I like how you wrote that program. Or you might say, that's horrible. I never want to see that again. But at least you'll understand that's the trade-off, right? That we're looking at. These were the things I was going to say. So abstraction, like I was saying, joins, group bys. These are cool, and they add some value in terms of programmer productivity, for sure. But they come at a cost. And in a lot of cases, in particular things like let's say PageRank or graph connectivity, these sorts of things, the several orders of magnitude difference there was because I wasn't able to get in and actually write the code that I wanted to write on those 100 computers. So what we've done in the past with Naiad in particular was exposed, I think for one of the first times, a nice low-level interface, still data flow, so it still fits in, integrates nicely with all of the existing stuff, but lets you actually write the code that you were really hoping was going to run in each of these vertices. So I'm going to say a little bit about these two things. Structured programming languages first, then the zero-cost abstractions. The structured programming languages, I'm going to work through an example of graph connectivity. If you guys have seen this before, that's great. I'm going to try to go, I guess, slow enough through it, so even if you haven't seen it before, you'll grok the main issues at least. But if everyone, to signal that you don't want to hear any more about this, everyone pull out your phones and start checking your email. It's very, anyhow. So one of the computations that people like to talk about when you have a large graph, I don't have a great motivation for this, but is graph connectivity. Which vertices in the graph are connected, potentially transitively, to other vertices in the graph? Is everyone in one large connected component, or are there lots of little sprawly, independent connected components? And this is very exciting for people doing viral marketing on social networks, or people trying to study the diffusion of information, or disease and epidemiology, these sorts of things, right? Those are the best examples I have. So One algorithm for doing this, and this is the algorithm that systems at the beginning of the talk were using for connectivity, is this label propagation algorithm. And the idea in label propagation is you have a graph, it's got a lot of vertices in it, and each of the vertices is going to maintain a label. It's going to maintain an identifier, which is initially its own name. But what's going to happen repeatedly is that each vertex is going to speak with its neighbors and exchange information, and essentially ask, among all of its neighbors and itself, who has the lowest label? What's the smallest label in that neighborhood? And it will adopt that smallest label. And now if everyone does this, and they do it repeatedly, the smallest label in any connected component will spread through the connected component. Eventually everyone will learn about it. Yeah? So we're going to write down that computation. I'm going to write it down in stylized programming language. This is actually a language that I've been using at the moment called Rust. Hopefully the right things are colored to look like functions, and the things that look like closures look like closures, but hopefully it looks a bit like Scala, or at least I'm told that the closure syntax does. So the way we're going to write this connected components thing, we're going to think about having a stream of edges. I've called it edges. This is a function we're going to write. It's going to produce a stream of labels. Label, I think of as maybe a pair of a node and a label. And think of edge maybe as a pair of a source and a destination, both nodes. The little bit of logic we're going to write is we're going to take the set of edges and we're going to apply a map to it. It's going to say, for each edge, let's have the source of that edge propose itself as a label. Basically, we're going to start out and we're going to give that vertex at the source a label that's its own name, just to start out. Then we're going to do some iterative computation. There's .iterate, and my understanding is that .iterate, I have a screenshot demonstrating this is true, that .iterate also exists in Flink. So some of you appreciate what iterate is meant to do at least, right? Which is to take a description of a Dataflow step, right? Something that you might put in the middle of your iterative loop. In this case, what we're going to do is say, if you give me a data set which is a collection of labels, I'm going to try to improve it. I'm going to do this little thing that I talked about where the vertices chat with their neighbors. I'll show you in just a second. I'm going to call it local min. Vertices are going to chat with their neighbors using the edges that have been provided, and they're going to improve their set of labels. So this is the local min implementation that I've sort of scribbled out, and I think it does approximately what I said, which is that you take your labels and you join with a set of edges. Right? So that join says, great, for every edge, source comma dest, I'm going to find the label corresponding to source, and basically I'm going to propose it to the person over at dest. Great. These are the first two steps. I'm going to concatenate in the original set of labels because you should be able to keep your original label even if you don't have a self loop back to yourself. And then we'll do a data parallel aggregation. This is sort of like a group by where we do an argument essentially. We ask, what's that one record for each of these groups that has the smallest label? Let's keep that. So that's one step in this local min subcomputation. And if we iterate this, we're supposed to arrive at a limit which is the connectivity structure of the graph. Basically, each node will have a label indicating the set of people that it's connected to. Great. Well, that's delightful. You can do this today. It works. It's great. Many systems are capable of doing this. In particular, they're capable of doing more clever things where each of these operators are incrementalized automatically, right? So that rather than telling everyone every single iteration all of the labels that are being shuffled around, you just tell people when they change, right? So as this iterative computation starts to converge, you send less and less data around. That's cool. Hooray! Excellent. We've written a function and it does what we think it should do. That's an important part of programming. We like that. There's some slight funny business here. Like, okay, well, what if I said stream, I didn't say set. So what happens if some more edges show up, right? And we can say, well, it's not so bad. Sort of scratch our chins and realize that if more edges show up, well, it's only good news from a label point of view, right? So if more edges show up, more people get to see even smaller labels. So yeah, maybe a bit more work happens, but we converge to an even better limit, and we do converge. There's a nice monotonicity property of this computation. But you might be a little worried now that we had to have a little conversation about that, right? That we had to sort of think and say, is this actually going to work out if new data show up? And indeed, it's only because computation has a certain structure to it. To make this a bit more painfully clear, there's some lack. I'm going to put this down here in the bottom, and I'm going to describe a few more computations that we might build on top of this connected components subroutine. So I called it connected components because if you run it on a symmetric graph or a graph where edges exist in both directions, it does indeed compute the connected components. But if you run it on a set of directed edges, so not necessarily symmetric, you get something potentially different. It's a label flooding algorithm that pushes labels forward along edges, but you're not guaranteed that just because two vertices have a directed edge between them, that they'll both get the same label. The downstream vertex will always get a label that's at least as good as the upstream vertex, obviously, right? Because it has the opportunity to push the label along. But the downstream vertex might have a slightly better one because, for example, you're not actually able to reach from the downstream vertex back up to the source vertex. This is just a little subcomputational fragment here that determines the labels and then throws away those edges that don't have the same label on both endpoints. Why would we do that? Well, it turns out, and I'm not going to necessarily try to convince you that this is correct, but if we repeatedly do this, if we throw away all those edges, they get different labels on each endpoint, flip the direction of the edges, do the same thing, flip them back. This converges to the strongly connected component structure of the graph. It's pretty cool. Strongly connected components, it's actually hard to do in parallel. Typically you do it with a depth-first search, and that's difficult to parallelize. This is a nicely parallel version of strongly connected components. Or at least it would be if it worked, right? I mean, let me show you the Dataflow graph. This is the Dataflow graph. There's cycles inside each of these connected component subroutines, but there's also a larger cycle that connects them all back to each other. And if we try to do our little head-scratching experiment now of like, well, what happens if we just start this thing running? Does that work? There's a bunch of non-monotonic annoying things. So in that filter by label, edges get thrown away just based on inequality, right? So they're not kept or retained based on some nice monotonic property that gets better or moves in any particular direction. One label could improve and you throw the edge away. The other label improves and the edge comes back. That's a mess. It's not guaranteed to converge or any particular thing like that. This is annoying because over on the left-hand side of the screen, we totally have like a relatively short sequence of methods that if we were to think, I'm going to implement this using an array or something like that on my computer, it would work. It would give us the right answer. Right? So there's some fundamental disconnect between our programming model on the left-hand side, where we wrote a program that has some intended output, and the Dataflow graph on the other side, which if you think about it as it works at the moment, it's just sort of a mess. It's going to compute who knows what without some more advice from us on how it should actually execute. So this is one of the points where I'd like Dataflow programming to become a bit more structured. Although we could have just a flat Dataflow graph that runs wild and crazy and just does as much data movement and processing as it possibly can, we actually want a bit more restraint and a bit more control to ensure that this computes the correct answer. And that's going to be important for us. We're not going to give up on performance, I promise, but a bit more structure. So what sort of structure do I mean? These connected components computations are confusing and weird, but if we cover them up and we just say, think of that as a vertex, all right? An operator. It's got some inputs, it's got some outputs, and there's a clear relationship between the supplied inputs and the expected outputs. Can we actually derive an implementation that respects that properly? Similarly, we might think of strong connectivity as having the same property. You can sort of think of it as a vertex with some inputs and some outputs, and there's an expected relationship between the inputs and the outputs. And it turns out that one very helpful way to think about this, or something that we've sort of thrown out there, or at least shown that works relatively well, is to take your graph and organize it hierarchically, just in this way that we described, where these subcomputations, you think of them as vertices. From the point of view of the strong connectivity computation, this higher level computation, these sub-connectivity computations, the connected components, they're just vertices. There's one loop. I haven't reproduced the figure here, but there's one loop that's going around. When we have to keep track of what iteration are we on, there's just one number that everyone in this blue scope is thinking about. But inside these green vertices, we have some more nested subcomputations, and they're going to have their own notions of iteration within them. So the hierarchical structure definitely suggests, suggested to us, a hierarchical notion of progress. So you make progress both in the outer scope, so there's potentially a coordinate indicating how many iterations have you moved around the outer scope, And an additional, when you are in these subscopes, an additional nested coordinate for measuring progress within the nested things. So I'm going to try to show you some suggestions about what this looks like now. So this is where the timely data flow system showed up. It was a way to deal with this type of problem of nested subcomputations, basically. I've tried to hint that when records move around, they're going to need to have these slightly more generic notions of time on them. I mean, you're familiar probably in a streaming system with like a timestamp on the records that sort of, as these move through the system, you can tell, well, how far along are we? What records have we actually seen? Are we able to go and release aggregates about various things? You've probably grokked iteration counters going around loops. You know, we're on the 7th iteration, 8th iteration. The data would maintain these as well. And as long as you just enrich this with enough information, so extend these iterations to contain 2nd, 3rd, 4th, whatever is necessary for the depth of the nesting information, you can write operators that see this data and behave appropriately. So you've taken what was a complicated sort of physical scheduling question of how does the data all move around, you've changed it to a logical question of, if I show you when this record was supposed to be processed, can you, clever operator implementation, figure out what you should be producing as output? And the answer basically is yes, just with more programming. So let me show you how you write an operator in this timely data flow thing. It's going to be fairly simple, the interface, but I'm going to try to assert, and I'm not going to convince anyone, I don't think, that it's actually possible to do a good job of this. But let me at least give you a flavor for what things end up looking like. So if you want to write an operator in timely data flow, there are 4 things that I'm going to put up here. First, you have to indicate to the system what happens when data arrives at your operator. That sort of makes sense, right? If someone shows up with some data and says, go, you need to say what should happen, right? But you're given some help here. You're not just shown the data, you're also indicated what time did it show up at. So you're shown particular records saying, Frank got label 37. But also, Frank got label 37 in the 3rd iteration of that strongly connected component computation in the 14th sub-iteration of graph connectivity. And that's interesting because I can say, well, okay, that's cool. I need to produce something for the 15th iteration then as output. And you don't need to worry necessarily about what other records are in flight or any complicated stuff like that. You can just locally do your work as if it were currently that iteration being scheduled. All right, you're also able to call in the method that you're writing here, send by basically. So you're able to send data at particular times. So in particular, I'd like to maybe send something for the 15th iteration because I'm in charge of aggregating up the labels and pushing something around the loop. So I might look and say, well, okay, that's an improvement in Frank's label. He used to be 56, now he's 37. That's pretty nice. Let me tell all of my friends about that. So I'll send that label out there, but I need to explicitly indicate the logical time that's being sent at. And this is a matter of bumping that 14 up to a 15 so that as it circulates around, the next person to receive it understands, we've made a little bit of progress. And the whole point of this, right, is to keep separate 14th iteration from 15th iteration from 3rd iteration. Instead of making this a big, horrible, snarly mess, we keep them separate. We notice when things first change. We notice when things stop changing in the 2nd outer iteration and then start moving into changes in the 3rd outer iteration, this sort of stuff. This becomes a horrible, disastrous mess without the next 2 operations, which essentially tell you about progress in the system. So you might wonder, well, thanks. I've received a bunch of stuff about iteration 15, but I can't really say anything until I've actually gotten everything from the 15th iteration. And to get that sort of information back from the system, you have another little bit of interaction with it. You're allowed to ask the system to notify you at a particular time. This is essentially saying, please call me back when you, the system, are able to convincingly argue that I will never again see messages with this particular time. So it's sort of like, one way to think about it is it's like registering a callback. It says when system makes a certain amount of progress, call me again, let me know. And because I've got stuff to do, right? I've got some messages to send. But because this is a weird and complicated system, at the point that I'm about to call this, I'm not ready to do that stuff yet. I don't think we've made enough progress in the computation. I need the system to come back and say, no, we're ready. Do your thing and send your data. Similarly, you need to supply a non-notify method that tells the system what should it do when such a time has been reached. And this is a slightly weird way. I mean, it's a slight inversion of control that's going on here. Normally, you think about, I'm going to write some code, and it's just going to read some records and write some records, and that's, rawr, look at me. This is cool. This approach is different, right? It says, I'll do some things, but I need the system to drive me, basically, right? I'm gonna ask for hints about what part of the computation are we actually in at the moment, and I'll respond appropriately. So you have to think a little bit differently when you write these vertices. It's a bit more of an event-based system, less of like an iterator model or something like that. But it works great. And to show you that it works great, this is that crazy computation. I'm just going to take a little bit of a break here and go over to here to do. So this is the strongly connected components computation running on my laptop. It's not a large computation that it's doing. It's about 1 million nodes, 2 million edges, but it's running this SCC computation, and what it's doing actually is every second it's screwing around with the graph. So every second, you haven't seen anything yet because I actually produced any output yet because it's slow to get going, but once it gets going, oh my goodness. So every second it's going to start manipulating the edges in the graph. I hope it starts. So historically this has taken 20 seconds. What have I done? Why am I doing a live demo in front of people that it's totally worked? Anyhow. Pain in the ass. All right. Oh, wait, hold on. Wait, why? Crud. This is because I scrolled up too far. That's why. I just killed it though. So what's going on is it took about 18 seconds to get going, and at the 0th logical time, it's, oh wow, there's 1.2 million edges that actually survived through this SCC filtering. But while it was doing all that nonsense, it was introducing changes at second 1, 2, 3, 4, 5, and we're recording over on the left-hand side. How long since we released those records into the computation has it been since we've actually seen the answers? And of course, 18 is the first because that's, well, I guess, before we get the results. But we started seeing the other stuff basically concurrently. So the seconds count down by 1 because they were released 1 second after we started. And the thing that you can see is when it finally clears, here at about epoch 18, the response time in this ridiculously complicated, so there's actually 3 levels of nesting of these coordinates. There's the epoch, the outer epoch that we're running through. There's the first iteration, and then there's nested iterations for each of these things. But we're still seeing sub-millisecond response times out of this. Not only sub-millisecond response times, but there are actual changes coming through the computation. So if it were doing nothing, right, if it were in the first step filtering out the edge and saying you're stupid, you could totally understand why it could come back so quickly. But this is actually pushing computation all the way through that silly Dataflow graph. And out the edge, make sure I killed it. Sorry before. No, I didn't kill it. No, okay. So we can admire it running. It gets old real quick. This stuff actually works. It's one of the cool things. The main limitation, just to be totally candid, is that it eats memory like no one's business. But that's okay because as we saw at the beginning of the talk, all these silly people went out and bought giant clusters and ran things like Spark on them. And instead, you can run our stuff, and it just goes really fast. So anyhow, thinking a bit more about how to structure computation so you actually get these properties that I think people want, where you write a subroutine, you look at it, and you say, I think my computation should do this thing. And I don't care about the fact that someone else has already used a loop in their computation. I want to be able to use a loop too, because that's an important part of programming. And maybe you agree, maybe you don't. So the second part here, and this is a bit more half-baked. This is stuff I'm currently working on, not Rust, but an implementation, Dataflow implementation in Rust. I like Rust a lot. If anyone wants to talk about Rust, I like to talk about Rust pretty much forever. It's a programming language, and one of the things that they have in Rust are the concept of zero overhead abstractions. These are basically the idea that you should be able to write interesting code using high-level programming constructs without suffering for it at runtime. So you should be able to use exciting things like generics, exciting things like iterators, what have you, and be assured that they're going to compile down to things that run basically as fast as they should. And I'd like the same sort of thing for Dataflow. So here's something from Flink. I don't know if you guys can read this, but here's sort of rhetorical. What do you think this code's doing? Right? I don't know if you can read it. There's some iteration. It says something something pages and ranks and okay. So it's doing PageRank, right? Right? So there's a surprise. Okay. So it's doing PageRank. That's good to know. That's helpful. Let's go to the next. Here's a different interpretation of the same question, which is what is this code actually doing? Like here's the running time. This is again just a screen grab from the same blog post. Yeah, it's 40-something seconds per iteration. It's on a cluster with a few machines. What are those computers actually doing? Because when I run this on my laptop, it takes 17 seconds to run per iteration. Something else is going on, clearly, right? And we'd like to, when you're writing a computer program, you'd like to try to figure out, well, what's really going on? I want to make my computer program faster. What do I need to change? What do I need to do differently? So, look at the program again. And I don't know. It's hard to tell, right? Like, I think there's a bunch of abstraction that's been put in the way, and it's hard to actually understand what's really going on in your computation, so that you could potentially figure. Maybe you can't fix it. Maybe there's just some fundamental decisions have been made for you about how join is implemented, for example, that make sure that your computer never falls over, but it does go a fair bit slower. That might be a fine decision to make. And I think this is maybe one of the places where people with a database background diverge from sort of my school of thought. We were having a conversation at lunch about this, where your main job as a person in the database space is to make sure that the computer doesn't melt down over the weekend because it's your weekend and you don't want to get a phone call. Whereas if you build systems, you want people to be able to write whatever program they want. And if a person's computer melts down over the weekend, that's great. You sell them another one. Everyone's happy. Well, anyhow. So, I come from sort of a school of thought where I want to be able to make the computer go really fast. I want to be able to get that stupid 17.5 seconds because I know computers can do that. How do I get that control back? So here's a different program for PageRank. This is in Rust. I like Rust. You don't need to understand too much about Rust except to trust me that when it says for something something something, it's a for loop. Right? It's not a complicated thing. This isn't a data parallel program. This is just straight line, the equivalent of straight line C. It allocates some memory. It does the sorts of things you do when you do PageRank. If you actually know what those are, great. I think this is supposed to have done them. It flips through the graph and it updates some locations in memory. And this is actually the code, literally the code that produced the 17.5 second number. And we can look at it and we say, good, yeah. You're updating some locations in memory, and I know about how long those take, and there's a many of them that you did, and this is very reassuring from understanding why your program did or did not take a particularly long amount of time. It's helpful in the other direction too, because you can, if your computer does something funny, if it goes slow or it runs out of memory or something bad like that, you can try to figure out from the code, okay, that was a mistake, I did something wrong, let me fix it. So again, like I said, I want more of this in Dataflow. Not necessarily everywhere in Dataflow, that's fine. We don't need to make everyone write programs like this, but I want to be able to write this type of program. So I'm gonna do that now. I'm going to take the core logic here, and the rhetorical device here is that I'm going to build up some scaffolding around it, and at the end we'll actually have a real bit of code that runs. It's also still going to be in Rust, but it's going to be a Dataflow computation that does PageRank for us. And I'm basically going to try to put in as little stuff around as possible to sort of screw things up, I guess is what I was about to say, but it's basically right. Like I basically want this code to run unobstructed. So what do we need to do? Well, we need to allocate some memory, right? We had those bits of memory that we allocated before. There's a slight tweak you might have noticed in that since this is going to be the parallel computation, we're going to need to talk about the number of other people helping us out in this computation. Right, there can be other people involved, and that's important to know so that we don't all do the same work that everyone's done. We're going to split the work up a little bit. In particular, we're only going to keep source ranks for some fraction of the data. And we're just going to do this round robin, so everyone gets a 1 over peers fraction of the pages. We still need as many destinations to aggregate into, because all of our little pages could point to anywhere in the graph, so we can't economize on those at all. But yeah, okay, so this is looking good. This is pretty similar to what we had before. The next reveal is a little scary, but I put comments on every line, so it's going to make total sense. So this is basically like what existed in the Flink example, in that we're going to say, I'd like to iterate a thing for a little while. I'm going to do iters iterations, and I'm going to give you a closure indicating what I want to do. But this is, this is sort of a boring closure, right? This is the closure that runs once when you set up the data flow graph. This isn't where the real meat is. Let me show you though what the closure does. It's very simple. It just says if you give me a stream of data, I'm gonna call this unary operation, which this is a data flow vertex. It's one that I happen to have written in a careful way so that the code doesn't change very much on the slide. But it takes two arguments. It takes an argument which, if you're a T Berlin person, it takes a parallelization contract. Yeah. So this says how data is expected to move around before it enters into the vertex. And this is basically saying, please do a data exchange. That's important. Don't screw that up. So we tell it about the data exchange. And then we basically just give it a closure saying, I'd like you to do when you run this code. Here, sorry, it's being a bit flip, but if you were to give me access to the input of the vertex, access to the output of the vertex, and one of those little control widgets that let me notify and receive notifications, here's the code that you should actually run. Tug on that little notification guide to say, are we ready to do an iteration? And if we are, go through and run my code exactly as written. At the end of it, I'm going to ship that stuff out through my output. And we have to put a little bit of additional gunk in there too, which basically this is saying, now that we've put all this stuff into the network, we should also probably pull it back out too. So tug on the input, and as we pull data out from the input, aggregate it up in our source vector. Right? And this is important because other people in the computation are sending us data, as we probably sent ourselves some data even. So this is essentially the moral equivalent of that loop where we reassign from dest back to source. And it's absolutely a bit more complicated than it was before. This isn't 5 or 10 lines of code anymore. But what this actually is, you can tell by all of the curly braces and close parens down. This is actually a complete program, well, except for the main around it. It runs. It's a data flow program. You might be a little disappointed because it really doesn't look much like a data flow program. But the main point is that this stupid unary operation, which you can, if you'd like, you can follow with some more joins and group bys and high-level constructs like that. It gives us the ability to dive in there and actually write the code that we want to have run in a vertex without any particular performance penalties. And this is, I guess, maybe a feature of Rust, probably also a few other languages. But this inner closure literally does just get inlined into the code that executes on the data flow system. And that's a nice feature. It's not wrapped up as an object and called through vtable or any nonsense like that. It literally is just code that gets splatted in there and executed. And we would expect the performance to be comparable. Well, sorry, I don't know what you guys expect, but it would be delightful if their performance were pretty close to this line. Now, maybe it's all screwed up. Like when I mentioned these numbers back from the beginning of the talk initially to the Databricks guys, Reynolds was like, well, it's graph computation's hard in data flow. You exchange lots of data. It's a mess. That's why we're 100 times worse than a laptop. Here's what happens if you run this thing again on my laptop. So maybe that's the secret. But it's in data flow. It actually exchanges, instead of just doing dereferencing into memory, it goes and exchanges all of these ranks. It writes them down into buffers. It sends the buffers around. And it's about 1 second overhead. Because, writing stuff into buffers takes time. It's actually doing the diligence of saying, well, even though there's just one thread at the moment, it does the diligence of saying, well, who do you want to send it to? Let me look them up. All right, I'm going to take that number mod 1. That's 0. Put it there, mod 1, 0. So it does all of that stupid computation, which you could get rid of, and the number would get a little bit smaller, but the point isn't to try to lie to you about how fast things go. But it's in data flow, so great. So you turn on a second thread. It goes down to 12 seconds, 12.3 seconds. That silly program that you just saw. And in principle, if you turned on more threads, it would get even better, except my laptop only has 2 cores, and the performance is actually at a point now where hyperthreading doesn't help. It's actually saturated the CPU, and we're not suffering memory misses. But this is, in my opinion, an example of where if someone wants to come along and actually make a nice fast PageRank, or a fast I've been doing fast relational joins as like a weird hobby for some reason like that. And it's the sort of thing that someone will absolutely want to sit down and get going really fast, because making a really highly tuned relational join is an important part of some like grown-up big data analytics sort of thing. And being able to get in there and cut out the factors of 10 or 100 that just doing a random hash join using .NET or .NET's what I used to use. .NET or Java hash tables is definitely an important part of that. So I'm going to basically wind down now, having said a bunch of nonsense that hopefully some of you will be a little bit skeptical about, but maybe think a little bit about and wonder, was there one part of the talk that actually I'd like some more of too? And again, maybe part of the talk you never want to see again in your life. That's fine. So we like simple programming models. We like these performant implementations. I'm going to just put the things that I would like to add on to them. Simple programming models which are enriched to really reflect the program structure, that say a bit more about the computation that we actually wanted to accomplish so that the system is aware of what actually needs to happen. You can go and spin those inner loops a little bit faster than it spins the outer loops, for example. That's an important thing the system can do. Makes your program go faster. And then performant implementations with these zero-cost abstractions, basically, ways of writing code that don't have to pass through the higher level abstractions that make decisions for you, but allow you to supply your own implementations. Maybe absolutely you can repackage them as your own abstractions if you'd like. Call it join and PageRank now and let people benefit from that. But would actually let you go and write these little things. And I think that's the last slide. Pow, yeah. So that's the last slide. One random comment just to throw out. Now, I hate doing advertising, but all of this code is actually up on GitHub if you want to play around with it. Like the Dataflow system in Rust is up on GitHub. The PageRank stuff may or may not. I could put it up there. I just haven't commented it or anything like that. There's some other cool stuff like that. But if at any point anyone would like to chat about how any of that works, that's basically what I'm playing around with now and for the next maybe month or so while I'm in Berlin. So, but anyhow, with that, I'll thank everyone and I'll be happy to take questions if people have them about whatever's going on here. Yes?
What happens to your program if you use a petabyte of data?
Sorry, what happens to the program if you use, you say petabyte? Petabyte's a lot. I can tell you what happens if you use a terabyte, because I've done that. So one of the initial complaints that showed up when we did when we took GraphX's measurements and reported them with the laptop numbers, people said, well, that's ridiculous. Those graphs are small, and they're a billion edges or something like that. They're not enormous. They're 6 gigs to 15 gigs of data. The slightly cynical side of me says, well, it's a very good question. Why don't you ask those GraphX people, because they're the ones who chose those graphs. But what I did was, well, let me look around for the largest publicly available graph that I know that exists. And this is the Common Crawl data set, which is about 128 billion edges. If you write it down just in binary, it's about a terabyte. Took a few days to download onto my laptop, but I downloaded it. And I have performance numbers for that. These numbers... Doo-be-doo-be-doo. I don't remember this. Drunken, there's a good story behind that. Here are the Common Crawl numbers. They're enormous, right? But the sort of cool thing to realize about them, so the Common Crawl data set is about 100 times bigger than Twitter. And if you look at the magnitude of the numbers, it's about 400 times slower. So it's about 4 times slower running on my laptop than you would expect based on the increase in the size of the data. And that's sort of cool because it's actually doing random access. There's 4 billion nodes, so it's doing random access into about 40 gigs worth of PageRank data. So it's paging like a beast, but it's running. It works. None of these systems, like here, these guys are going out of memory on a graph 1/50th the size. Anyhow. Yeah, I don't know what happens if you go up to a petabyte. I'm pretty sure I know what happens to these systems if you go up to a petabyte. Just to say, not very much. So that's a very flip answer. Maybe a slightly more productive one is that in making the Common Crawl stuff actually work, one of the important optimizations that you do is you lay out the graph slightly differently. So use what I used at least, was a Hilbert space filling curve, which happens to be a very cache-friendly page layout, and you would totally be able to process, if I were able to fit one on my laptop, you'd be able to process the petabyte of data. It would take 1,000 times longer at least, but the cache behavior of it is absolutely delightful. It works wonderfully. I have no reason to believe what a horrible way to do science. I have no reason to believe that it wouldn't work if you just gave me more machines. You're right, okay. I'm talking nonsense. So yeah, I haven't tried anything on a petabyte of data. I'm not going to be able to in the near future, and you should not buy anything that I'm selling you. Seriously, like, for money. So you should believe the things I have to say. But there's a huge difference between stuff that runs on my laptop and munges some data and points out some deficiencies at a certain scale, and a real system that's engineered to not fall over at a totally different scale. Other questions? Yeah, go for it.
So you point mostly graph use cases. So does it work also for other use cases?
So the question.
Also talk about relational stuff.
Yeah. So the question was, I spent a lot of time talking about graphs. Are there other applications where any of this is in any way relevant? And this is a good question. Relational joins happens to be a particular area. If people follow the literature, there's some awesome stuff going on there right now. So there was a result from about 2 years ago where some theoreticians, actually, this is really cool. Theoreticians pointed out that the way people have been doing relational joins for the past 40 years is asymptotically suboptimal. So the traditional approach to doing joins is you form a tree of binary joins. Sort of a system R-style optimizer. You figure out the best arrangement of all, but no matter how you arrange these stupid binary joins, you can always prove that there are going to be inputs that can force the relational join to produce way more records than mathematically it's possible for the join to produce. And they came up with algorithms that are asymptotically optimal in the worst case sense, but they're weird and crazy and different. Right? So they're not just a simple vertex per join that you stream things through and keep a lot of memory. They're interesting and sort of different. They require slightly more progressive thought in Dataflow, let's say. So you have to be able to write slightly weirder Dataflow computations. Actually, I think Flink would totally be up to the task, but it's a matter of actually sitting down and engineering it. And it really is a matter of getting these overheads down to basically zero, because what they do in their core is a bunch of intersections of sorted lists, and it needs to be really fast. So the way they're doing it at the moment is SIMD intersections with 256 wide registers. So that's the sort of performance that they're trying to get. There are lots of other areas that people are looking at, analytics of all sorts of flavors, and it's a good question. I mean, graphs are weird, and that's one of the reasons that there's a lot of potential for space between what's currently being done and what you can do if you're clever. If you want to talk about how fast can k-means be made to go, for example, I don't have anything special to say there, right? I mean, that's a loop. You update a whole bunch of stuff every time around the loop. I don't have any magic sauce that makes that go fast. Or if people are going a lot slower than for loops at the moment in k-means, that's a real problem, and you should be very rude to those people. But yeah, it's a good question. I think mostly this is forward-looking in the sense that I'm optimistic that more and more interesting computations will be brought into the fold, and we'd like to support them. grep isn't going to go any faster because of anything that I've told you, but that's still going to be a very important thing that people are going to want to be able to do. So, yeah. All right. Other sorts of questions, Stefan. Yeah.
So two different questions. First one, the way you implemented the algorithm is pretty much, it's very different than all the other systems that implemented, right? You sort of random memory scattering of your updates and so on, which is something that you can do on your one machine as soon as you start going to many machines. Your problem system is probably also going to take a hit once you start actually parallelizing it and have to start scattering network buffers and sort of shipping them, recompiling all the stuff. So there seems to be sort of this really sweet spot for one machine computation, like in particular.
So I can repeat that question and give an answer to it, or I can let you. Yes. Sorry, I mean, there's no question mark at the end, right? The question mark is like, well, yeah,
Yeah, okay.
Right.
So then how far do you think these results, is this like a very extreme case in your opinion, or do you think for many more computations you can sort of draw the same calculus?
All right, so first question at least is, things are a lot easier on a computer, especially in the context of buffers and stuff like that. If you can fit everything in memory on your laptop, that's not going to change. You're not going to get memory exhaustion. You're not going to have these sorts of issues.
You don't have to start dealing with the network synchronization
Absolutely right. So at this point, I'm just going to invoke my credentials of having worked with all the nice people on Naiad, where we happily scaled things up to hundreds of computers, and it still went at nice blistering fast speeds. I think the main.
I mean, I granted that you can sort of like scale the differential data flow to a lot of machines, but I mean, are you going to see the same differences in speed for, let's say, anything else but, let's say, nested iterations?
Good. So I think, so the question is, okay, will you actually see these same performance benefits at scale? There are a few things. I think one of them, absolutely yes, in that we're able to put data from in-memory buffers onto the network super fast. This is only going to get faster. If you read about all the nice, wonderful advances in RDMA, stuff like Rocky, 40 gigabits, 100 gigabits is really fast. I mean, it's just, and the fact that you can get into another computer's memory in like 1.3 microseconds with provided libraries, basically, the code that other people have written, so you don't have to get it wrong, is really nice. I mean, you can really saturate really, really thick links. And one of the really nice things about Dataflow, as opposed to other systems like RPC or something like that, it's really simple. You just, there's a unidirectional pipe. You put stuff in a buffer, you send it, you wait for it to go, and if the networking people have their stuff together, it just works. And that was almost our experience with Naiad, with some caveats where the networking was initially tuned for wide area networks, and we had to go and we had to kick it for a while. But there's a second issue, which is that a bunch of these weird computations, graphs in particular, have nonlinear scaling properties, and that's interesting. So you add more and more machines, the amount of communication they have to do doesn't go down linearly. It goes down by a factor of the square root of the number of machines in the case of most of these data exchange in graphs. So, so you're not magically going to get linear scaling all the way out, for sure. And I suppose the response there is mostly that, look at these numbers, right? Like, if you could get single laptop performance on just one of the stupid machines in the cluster, you'd be delighted. You'd have gotten a 20x improvement already. So we can wonder about, is it really going to make sense to scale quite so beautifully out there? The reason these systems are scaling well is because they have so much CRUD built into them, right? Like, they do get linear scaling, but the things that they're parallelizing are just overhead. You shave away that overhead, and who knows if Spark actually gets faster when you add more machines. When you take away the fact that it does all sorts of nonsense. It's a good question, and I'm not going to accept responsibility for the fact that Spark has set everyone's standards to be delightfully low. It sounded really defensive. I'm sorry. I think it's good to make sure that you sort these things out to things working in the cluster. They're not solved in any way, and they do raise a bunch of interesting questions. But I think a bunch of the restrictions that Dataflow imposes on you make the problems a lot easier to solve than they used to be. It also allows you to focus your attention a lot more. Like, you can start to focus. Let's make the network transport really nice and sweet. Let's invest a whole bunch of money in whatever your favorite 0MQ or nanomessage or whatever type of transport. I don't know if any of these things are popular nowadays. They're buzzwords. All right. I'm going to stop there because I'm just rambling. Go for it.
Well, what I have seen is that basically these operations are extremely simple. You're just going through a huge bunch of data and just doing basically nothing with the data, just sorting or something like that. And I think really for where I work, there I haven't seen the huge benefit of all these jobs. It's more, well, basically it's a benefit when the data is too big that you can store it in the memory of one of your computers, because when disk swapping starts, the performance of a machine goes downhill pretty fast.
Yep.
So I would only use any kind of multiprocessing when I have any ability to get my data into the memory of one machine. I would just do it and not try to do some MapReduce stuff.
Yep.
And on the other hand, when I have an expensive process per record, where I do a lot of calculations and stuff, where I'm doing stuff on that record, which is really, uses lots of CPU, then it is, of course, useful to have lots and lots and lots of cores just to do this stuff and parallelize. And I use the Hadoop more to manage the overhead and the distribution of the data rather than trying to compute anything with the MapReduce.
Yep. So you make a good point, which I'll summarize at least in my take on it, which is that another very good reason to be using scalable systems is for capacity. So you can try to make your system go 10 times faster by using 10 times as many machines, or it can just bring you to the point where you can actually do the computation that you need to do efficiently, because you couldn't do it on 5 machines. You didn't have enough memory there. And that's wonderful. This is a great example of superlinear scaling, where if you look at the performance for 5 and you go to 10, it's more than a factor of 2 improvement. It's delightful. I think the thing that I would say there is you're absolutely right, and one of the things that people should be looking in that case, this is even more of a call to pay attention to overheads. That if you're storing, you're using some nice Python distributed data processing platform, and you realize, wow, everything's being stored as a string because I have like 1 string in my dictionary. They were supposed to be bools, but now they're strings. Like paying attention to these sorts of things. I'm sorry, I didn't mean to suggest that's what your life is like, but paying attention to these things, trying to really bring down the overheads, takes you from needing maybe 100 computers down to needing only 10 computers, or if you're lucky, down from using 10 to 1. And it's something to pay attention to. If you don't have this problem at the moment, great. But some people definitely do have the problem, and basically just try to call attention to that. Yeah. All right. I'm not going anywhere. So if you have questions or things you didn't want recorded or read back to you, I'll be around. But thank you again.